going to go for it anyhow. All right, so first thing says, consider the data set below comparing birth rate and female life expectancy in countries around the world. So number of births per thousand population and female life expectancy. So it says create a least squares regression line. That is a fancy term of saying go to Desmos, make a table, and plug your data in. All right, so you guys were doing well with this. I only had one person that goofed this up on the Quizaroo. Okay, so hit the plus. It's got to be my kids. Not my kids. All right, let's see. I have 31.1, 62.4, 48.6, and 54.9, 49.2.
Wait, isn't Skylar on the Spirit bus?
Skylar's right there.
Oh, not Skylar. Coco.
Yeah, 60.9. And 45.2. 45.2 goes along with 59.2. I need to help myself out. Things are wobbling around in Stirrup's head. 45.2, 16.9, 16.9, and 75.7. 51.8 and 58.7. 26.1. 72. 42.6. 64.3. Okay, I feel like I'm doing this forever.
Like, how do you think we feel, Stirrup?
Okay. 72.8. 13.0. 72.9. 23.9. 73.1. Sounds like a party out there. We're missing out. 36.7. Guys, go take care of the light work out there, would you? All right.
Why are people so loud? God damn.
True. All right. So looking at it, it appears to have a negative correlation. Why is that? Negative slope. Oh, look who came.
Hey.
What up? What up? Yeah, you already know. All right.
I was gonna wear a 90s jersey, but I thought people were gonna disrespect me from saying, oh, we found jersey day. Well, guess what? He played in the 90s. Wow. Whatever. Hey, Lionel Messi's in the 2000s.
And for those of y'all that just came in, we are on page 139. All right. Shh, bring it back together. So, create a least squares regression line. The rest of the fellows are in the house.
I get. My dad took it from me. When my aunt got to me for Hanukkah one year, and my dad's like, "No, you are not going to make him that jersey."
All right. So what's next? How do I get my line of best fit? How do I get my line of best fit? Page 139. How do I get my line of best fit? How do I make the equation? Anybody? Anybody? Y1 tilde mx1 plus b. Talking to myself up here. All right. Does it make sense that the R value is negative? Yeah, it's a negative slope, so it should be a negative line. So basically, if I were to plug this in and make it 100% appropriate, I would have negative 0.46. B is 81.7. 81.7. All right. So if I wanted to create the least squares regression line, now I'm not going to dock you for this, but I just want to make sure that you feel comfortable with how this should be written. Okay, we are used to y equals mx plus b. Agreed? So if you gave me an answer like this, negative 0.46. Negative 0.46 x plus 81.7. Technically, you're correct. In the world of statistics, they would want it like this. Negative 0.46x. Oh, it stopped working. All right, so they would want it flipped over. Okay? You can't read the language up there. It's because it's now doing its thing. I guess the update didn't work. Darn thing. All right, so basically in the world of stats, you want to have y hat. This means that this is going to allow you to make predictions. They flip this over. Okay, they don't change. They don't put the 81.7 with the x. They just put the 81.7 first, and then they put the slope second with the x value. And interpret the slope in the context of this question. So it appears that you lose for every point, you lose 0.46 years of life for every one extra person born as far as this takes place. Okay? So that's the slope. Interpret the y-intercept in the context. If 0 people are born, then the average life expectancy would be at 81.7. There appears to be a negative association between husband age and wife's age. Explain briefly what this means. I don't think we have a husband's age up there. So I think we can skip number 5. Number 6 says a certain country has a birth rate of 9.6 births per 1,000. 9.6 per 1,000. So what you're going to do on that is you're going to plug 9.6 in. So I can go negative 0.46 times 9.6 births plus B plus 81.7. So if you do that math, oops, I have an extra decimal that didn't need to take place. So let's see, what am I off there? Oh, I forgot a decimal here. That's 4.6 or 0.46. 0.46. All right. So is the point 9.6 comma 77.82? You know, is it extrapolation? So let me put what this point would be. Okay, I'm going to make a table again. And we'll do purple dot. So 9.6 and 77.3. Okay, so notice this purple dot right up here. You look at the purple dot. Is there data to the right of it? Yes. Is there data to the left of it? No. It's extrapolation. What did I say about extrapolation and statistics, friends? It's bad. It's not to be trusted. Okay? Not to be trusted. And I think I can go through the rest of these. Let's see. On page 140, number 7, is there a positive or negative association between the two variables? It's a negative association because the graph is going downward. Okay? And then the summary of the regression line shown in red. We can't see red. They have basically the equation 45.64 minus 0.005 times the weight. Interpret the meaning in the context of this problem. So it appears you drop 0.005 miles for every 1 pound of weight you add to the car. Interpret the meaning of the y-intercept. The y-intercept would be if your car didn't weigh anything, or if you got, let's see. Interpret the y-intercept. If your car did not weigh anything, then you would get 46.6 miles per gallon. This is extrapolation. It's outside of our data. It's bad news, so we can't trust it. It gives us an awkward answer. Yes, the y-intercept is extrapolation. It's outside of our data because we don't have any values that are 0, comma anything. That was 8 and 9. Is the y and 10. Okay, so it's extrapolation. Number 10 is extrapolation because the y-intercept is outside our data set. And if you were to buy a vehicle that weighs 1,000 pounds heavier than the vehicle you have now, does a regression model predict the amount of change for gas mileage? Well, first off, you would have to know how much your car weighs. I guess you could Google that. And if you bought something that was 1,000 pounds more, I mean, honestly, if you were to go 1,000 pounds more on our line of best fit on there, we are underneath. So we're getting like negative miles per gallon, which that's probably not good. All right. So let's go back to 2-6, the lecture. If you're here, I'll put that in. I figured some of you probably had done it, and then some of you are probably like, wait a minute, we had homework. Yeah, I did assign homework on Tuesday night. I'm sorry that you didn't get the memo. So let's bring this up again, see if we make this keep working for us. All right, 2-6, visual interpretations of regression models. So I'm on page 41, So it says that each of the data points are from 1 to 20. This helps us to discuss the relationship between various data points and the regression line. Note that some data points are above the regression line and some are below. Some are very close. Each data point is an actual observation. So if you look at an individual at number 11, produced a score of 8, the creative score of 7, this result would be recorded on the scatter plot along with 19 other individuals. The linear regression line absorbs all these observations. So what that basically means is this. And let's just go back to Desmos. If we were to look at this type of problem, I realize this isn't the one. Notice you have some of the points that are on the top right, some are at the bottom left of our line. Okay? That is all taking place. It says the regression line, and my regression is different because I'm just using Desmos. But if you were to go and look at all of those, there is a certain distance, a vertical distance above or below my lines. So note that there are 10 observations above the regression line on the page that's shown. And we would look at the corresponding Y on the regression, not the other observations. It's interesting to note that person number two scored slightly higher than the regression line. Okay, it is interesting to know number 2 scored slightly higher than the prediction that person number 6 scored somewhat lower on this prediction. That's what's naturally occurring. there are 10 observations that are above the linear regression model. Just counting, going above it. Their actual creative score was higher than the regression model predicted. Okay, so what this is meaning is this. Let's see if we can make this work. We have something that looks like this, and we have 10 values that are above, and then we have some values below. This blue versus this green means that the blue, that data point is above. That means that my line of best fit did not predict, it under-predicted how the person actually did there. The green line means that the regression line over-predicted how that person would have done. Okay? So, let's see, I think I know where this is going. All right. So, let's go back to Desmos. I'm going off this screen. Okay? Remember that residuals that is there on our line of best fit? Okay? What the residual value is it will post things along the x-axis. The residual value is going to be above the x-axis, whatever this distance is, and it'll be below the x-axis, whatever this distance is. So if I went and I said, okay, I want to plot the residual values, and then I have to move this down a little bit. Oops, let's come out a little bit. Okay, let's see if I can make this more clear. All right, do you see the green dots for our line of best fit? Hopefully. Do you see the red dots down at the bottom? So basically what this means is if I go to any one of these points, like this green plot right here is below the line. So it's slightly below the line. The distance vertically it's below this line is the same distance as down here. And I believe on Desmos you could actually click on the data point and it's going to tell you. So that was at 13. This one here was at 13. Okay? So what's taking place is this. For that exact value at 13, my data that I put in, the dot, was a under prediction of what the line of best fit said it should have been. Okay? The line of best fit right here, if I could find the value at 13. Come on. Oh, shoot. So 13, if I plug 13 actually into my equation, I'd get roughly 75. That basically means that my data was undervalue, or my, let me think about how do I want to say it? My line of best fit is going to make a prediction within my data, which is interpolation. Okay, let's come to something that's truly inside of our data. Let's go to this point here, 31.1. I'm going to come straight down here to this one. This also should be 31.1. Okay. Oops. There and click here. All right. So if I were to make a prediction based on this point here, this is underneath my line of best fit. That means the line of best fit, if I plug 31.1 in, I would get a dot into my equation. The dot would fall right on this line. How far away from that line am I? If you move down here, we are almost a distance of 5 units below the line. So my line of best fit would be an over prediction based on our data. Our line of best fit would be an under prediction if we had a point that was above the line that we were talking about. And that's really all that's taking place. Now, the nice thing is the residuals, Desmos does it right away. All you have to do for the residuals is just, click. I don't know how I can undo the residuals now. But you hit that little button here, and it's going to you have to find your x-axis, and it tells you the vertical distance above or below. If the residual value is 0, that means that my data point fell exactly on the line of best fit. Okay? And I don't think I have any that fall exactly on it. If I did, I would have a point that would be exactly on that line. Okay? That's the ins and outs of this stuff. So let's see what 2.6 has to offer us. All right. So I would like you to give the opportunity to work on page 141, 142. You have the period to finish it up. You get done, you don't have any homework. Sound good?